Everyone, we're very happy to have Shai Chester visiting us from Harvard today, and he'll be telling us a bit about pure supergravity and the conformal.
All right, thank you for the invitation. This is based on a paper from several months ago with Vander all day, as well as many previous papers I'll discuss through the talk. Okay, so let's start with general discussion of quantum gravity. What is quantum gravity? So as everyone here knows, gravity is non-normalizable. So this means that quantum corrections induce infinite higher derivative corrections to the Einstein-Hilbert action, which you write as R. So if this is the action of gravity, so this is in d bulk spacetime dimensions. So we have the Planck length d, LD, and then we have a leading term R, which by dimensional analysis is multiplied by L squared. And then because it's non-normalizable, once you start adding counter terms to take care of loops, you will generate these high derivative corrections, starting with R squared, and then including R cubed, R4, etc.
I thought there is no R squared.
Well, it depends on the bulk spacetime dimension. I think it's specifically in 4D. I think you can kind of get rid of it, but
I thought the equation of motion is just R equals 0.
perhaps it's not an R squared yet. So, but like generally speaking, there are high derivative corrections, and so the coefficients of these high derivative corrections, though, are unknown a priori. And so what it means to have a UV complete theory of quantum gravity is that it should be some theory which tells us how to fix all these coefficients kappa of the infinite high derivative corrections which are induced by loops. And so if you can do that, then you have a UV complete theory of quantum gravity. And so there are only two such UV complete theories of quantum gravity that we know of, which have massless particles of spin 2 or lower, which is what we want because that's what is physical. And in particular, the known completions are string theory, which exists in 10 dimensions, and M theory, which exists in 11 dimensions. And of course, these are related by dualities. So really, there's just kind of one known UV complete theory of quantum gravity. The problem, though, is that it's hard to compute these higher derivative corrections in practice for string theory, and even in principle for M theory. So for string theory, we have a world sheet. So in a string coupling expansion, we would know how to compute such higher derivative corrections. But for M theory, we don't have a world sheet, so we don't even have an in principle method of computing higher derivative corrections. And even for string theory, if you want to go beyond just the perturbative in string coupling, if you want to look at finite string coupling, we also don't have an in principle method of computing higher derivative corrections. And so even though we might think that we have a UV complete theory of quantum gravity for the last 50 years, it's much more limited than you might have thought, because we can't even compute the most simple aspects of a quantum theory of gravity in general. And so the thing which kind of saves the day, as often in quantum gravity, is ADS-CFT. So if we look at quantum gravity on ADS, i.e. negative curvature spacetime, then the solution to this problem is given by ADS-CFT. Yeah, question?
Could you remind me how both the G string and the alpha prime expansion would appear in that first slide?
So here I'm just doing an expansion in the dimension-full coupling. So it's like, I think this is a low energy expansion. And so it would just be an alpha prime expansion. So like so in the context of string coupling, you would imagine this finite string coupling. So I'm just talking about just like the low energy expansion. And so the claim is that if you're doing finite string coupling, then even the world sheet doesn't help you because that only gives you perturbative string coupling.
So kappa is a function of the string coupling, but not of the string length.
No, it's a function of the string length. Yeah. Because it's the dimension-full parameter.
Okay.
Yeah, so it's just a low energy expansion. So there's a unique low energy expansion. So for M theory, all you have is this low energy expansion. For string theory, you could in principle also expand in the string coupling if you want. Okay, so in the case of ADS, ADS-CFT helps us. And so just to review, the most well understood examples of ADS-CFT is when you have maximal supersymmetry. There are 3 such cases. So when you have M theory and ADS4 cross S7, that's dual to a 3D CFT called ADGM. When you have type IIB string theory and ADS5 cross S5, that's related to n equals 4 super mills, 4D CFT. And when you have M theory and ADS7 cross S4, that's dual to a 6D maximally supersymmetric CFT called the 2,0 theory. And so in this duality, graviton scattering in the ADS quantum gravity is dual to correlators of the stress tensor operator in the CFT. And so you have this program where if you want to recover flat space scattering, known as the S matrix, which is at least on shell is in one point correspondence with the effective action from the first slide, then the way you can do it is that you start by studying the CFT in some 1/n expansion, and that is dual to scattering of gravitons in ADS, which is the scattering within a cylinder, because the cylinder represents ADS. And then there's a precisely understood flat space limit worked out by Pedodonis, working, following many previous authors, which tells you how to go from scattering in ADS to scattering in flat space. And so this in principle tells you how to go from a 1/n expansion in CFT to working out the coefficients of the higher derivative expansion for your theory of quantum gravity. And so this is why ADS-CFT kind of solves this problem of how do you compute the corrections to Einstein gravity coming from your theory of quantum gravity, at least in principle. But of course, doing this in practice is very challenging. And so now let's focus on a specific physical problem, which we would like to address. And this is the problem of scale separation. So in all known cases of ADS-CFT, the radius of the compact spacetime, so for instance, when you're doing ADS5 process 5, this would be the S5, is the same as the curvature of the ADS. So another way of saying this is that the extra dimensions are large. Because we would think of ADS as like the physical, spacetime, and then the S5 is like the extra dimensions which are compactifying on. And so this makes these well understood examples of ADS-CFT unphysical, because if we were to eventually want to relate string and M theory in 10 and 11 dimensions to what we observe in 4 dimensions by some kind of compactification, we would want the extra compactified dimensions to be very small, which would explain why we don't see them day to day. Whereas these canonical examples of ADS-CFT are kind of the opposite regime, where the extra dimensions are as big as they possibly could be. And so the question is there a UV complete theory of quantum gravity, focusing on ADS, the best understood toy case, such that these extra dimensions are small? And so in this talk, I will show that pure supergravity, which I define to be a theory of quantum gravity on ADS with no compact spacetime factor. So this is the most extreme case of scale separation, where one scale is just 0. So this theory of pure ADS supergravity saturates the most general conformal bootstrap bounds on ADS graviton scattering, which we verify at 1 loop order in this low energy expansion. And furthermore, I will show some intriguing evidence that these numerical bootstrap bounds might be able to define pure supergravity even non-perturbatively in the energy, which is a very bold claim. And so I'm not going to put all my money on that, but there's some intriguing evidence in that direction. So in particular, you could in principle maybe fix all the coefficients in the higher derivative corrections to Einstein-Hilbert action, maybe from these numerical bootstrap bounds. And so that's going to be like the claim of today's talk. So I guess before I jump into the details, any questions about the introduction?
I think I'm still a little confused about
Okay.
this. So say even at the CFT at large N, you'd still have the coupling, the 't Hooft coupling.
It depends on the specific.
It
It depends on the specific example of ADS-CFT. So you're saying in the context of n equals 4
Yeah,
squared.
for example, right? So
Yeah.
it's just the purely classical level, we'd have the whole alpha prime corrections.
Well, sorry. So
The
what?
higher derivative alpha prime corrections.
Okay, so if you want to do a low energy expansion in the bulk, that is equivalent to the 1/n expansion in the CFT. So there's no reason to consider the 't Hooft couple. So like n is what corresponds to Planck length.
Right.
And then G-Mills is what corresponds to string coupling. So let's just forget about G-Mills, we can make it finite. And so the 1/n expansion in the CFT, that is what is related to the low energy expansion in the bulk. And that works for any example of ADS-CFT. N equals 4, ABGM, 62,0, doesn't matter. So what people call the strong 't Hooft coupling expansion is specific to the case of type IIB string theory, such as N equals 4 spring mills. And in that case, you're essentially doing a 1/n expansion and then also doing a small string coupling expansion on top of it. But more generally, there's no reason to also do a small string coupling expansion. You could just leave it finite.
But I guess if it is finite, then there are many additional light fields in the bulk in general. And
No, I mean, you still have a geometric limit. The only thing we need for geometric limit is the low energy expansion.
in the limit of 0 coupling, wouldn't you get many additional light fields?
No.
It would be dual to a free theory.
No.
It has higher spin currents.
No. So that's a different limit. So like the free theory limit, so it's like it has to be kind of like an order of limits thing. So it's like if you're doing large n, I guess like in principle you could look at super small coupling, and then I guess there would be some kind of like free theory expansion. But for any finite value of the coupling, the large n expansion is just a low energy expansion, and the only light fields is the gravity. And in particular, the lowest few coefficients of this high derivative expansion have been worked out at finite string coupling. So for instance, the R to the 4 correction, its coefficient is known to be a function of tau, the complexified coupling, and it's a non-holomorphic isotensor in particular. But there's an order of limits where like you can't just then take if you try to take then like the weak coupling limit of the non-holomorphic Eisenstein, it diverges, and it just shows that like the limits don't commute of like doing large n and then doing Any further questions? Okay, so let's dive in and maybe some of these questions will be addressed by the details. So the outline of the talk is that first we're going to start with some kinematics of the stress tensor correlator and a maximally supersymmetric CFT. Because we're doing maximal supersymmetry in the CFT, we're going to restrict to dimensions 3, 4, and 6. Then we're going to discuss how this 1 over n expansion of the CFT is related to the small Planck length expansion of the holographic correlator, which you could think of as just a low energy expansion. Then we're going to discuss how to get one loop from tree level. And then finally, we're going to discuss these numerical bootstrap bounds for the various dimensions we consider and how they relate to the bulk tools. Okay, so let's start with this general stress tensor correlator kinematics for the case of maximal supersymmetry. So as usual, when you have supersymmetry, it's convenient to consider the superprimary, which for the stress tensor multiplet is a scalar we call S, which has dimension d minus 2. And so we consider the 4-point function of this superprimary. And as usual in conformal field theory, we can factor out this x dependence such that the 4-point function is written as a function of u and v, which are the two conformal cross ratios. And so we should think of g of u and v as our 4-point. So by taking the OBE twice in this 4-point function, we can expand it in blocks. And because we have supersymmetry, these are superblocks. So you have a different superblock GM for every supermultiplet that appears in this OBE, where the GMs are totally fixed by kinematics. And so some non-perturbative things we know about this 4-point function. First of all, unitarity requires that these OP coefficients squared be positive, which will be useful for the numerical bootstrap. And then secondly, because we're working Euclidean space, these operators commute. And so instead of taking the OPE of 1 and 2 and 3 and 4, which is what gave this expression, we could also take the OPE of say 1 and 3 and 2 and 4 or any other permutation. And so demanding that these different permutations be equivalent gives you what's called the crossing equations, which is an infinite set of constraints. Because you're saying that this whole function of u and v is equal to that function with v and u switched with this overall factor. And so this is a very powerful set of infinite constraints. And as I will describe in more detail in a few slides, this is basically what powers the numerical bootstrap. This infinite set of constraints combined with positivity of OP coefficient squared. And I should just want to emphasize that all of this is something we know for general CFTs. So we don't have to make any assumptions aside from the fact that it's unitary. So the generalities. Okay, so how does this relate to bulk quantum gravity physics? So let's imagine we expand our 4-point function in the large C regime, where C is defined as the coefficient of the canonically normalized stress tensor 2-point. And so why is it convenient to think of C? 2 reasons. So from the CFT perspective, C is inversely proportional to the stress tensor OB coefficient when we unit normalize S. And so this means that there's a way of inputting C into the bootstrap in some kinematic way. And so we can use C as kind of like a dial to dial, which theory we want to look at, big C, small c, etc. From the gravity perspective, and also from the CFT perspective, C also counts the number of degrees of freedom in a given theory. And so that's why it's useful to consider an expansion in this parameter, because it's basically proportional to n. So for instance, for n equals 4 super Mills, C goes like n squared. In ABGM theory, it goes like n to the 3/2, and the 6T theory goes like n cubed. And so the large n expansion is basically the large C expansion. Except C is the kind of the more natural parameter, which is why we're going to be discussing large C in this. So now from the gravity perspective, we can relate the C to the ADS parameters, i.e. the Planck length for bulk spacetime dimension D, as follows. So it just follows from dimensional analysis that C is proportional to LADS divided by the Planck length to the power d minus 2. Such that the large C expansion is dual to the small Planck length expansion, i.e. the low energy expansion. And the reason why you get d minus 2 is simply because the Einstein-Hilbert term has length dimension 2. And so you have kind of like the full length dimensions minus 2, and then the coefficient just follows from dimensional analysis. So it was shown by this very nice paper by Rosselli and Zhao from a few years ago that if you have bulk Einstein gravity, then in the low energy expansion, so assuming no higher spins, you can severely constrain the 1 over C expansion by the following very general constraints. So crossing symmetry, which is something we know to be kinematically true, supersymmetry, which is also just a kinematic constraint, and then lastly, something which follows from large n, what we call analyticity, which is another way of saying that only certain Witten diagrams are allowed at a given order in 1 over C. So, for instance, at tree level, so the leading order in 1 over C, the only Witten diagrams you're allowed is single traces for the graviton multiplet, because that's your only light single trace multiplet, and then also double trace exchange. But at tree level, you're not allowed to have triple trace exchange or higher. And then once you go to higher loops, then you're allowed to have, maybe triple trace, but not even higher trace. So this is just the general constraint of large n factorization. So the point is that just from large n factorization, as well as these general kinematic constraints, you can severely constrain the functional form of your 4-point function in this large n, i.e. large C expansion. So let's give an example. So we're looking at our 4-point function in a large C expansion in a general bulk space-time dimension D, and this is what it looks like. So at infinite C, you just have the disconnected term, which is totally trivial. Then you have the tree level supergravity term, which is why I read it as GR. Each of these G's is a function of U and V, which I claim is totally fixed by these general kinematic constraints. And so this thing is totally fixed. Then you have a one loop term coming from vertices, which is just this Einstein-Hilbert gravity term. So that's why I read it as RR. So this thing is also totally fixed, but there's a contact term which you cannot fix based on these general constraints. And that's why I write this kappa. This is some numerical coefficient, which is as yet unfixed. So it's not just fixed by these general constraints. So then on the lower lines, I write the higher derivative corrections and how they contribute to this formula. And so the reason why you have this funny fractional power of C is that just follows from dimensional analysis. So for instance, if you're looking at an R⁴ correction, this is 6 units of length bigger than R. And if you translate a unit of length into a power of C, it turns out you get this power of C. And so these general constraints fix the functional form of the R⁴ coefficient, of the R⁴ function, but they don't fix the overall numerical coefficient. So this B is a numerical coefficient. In order to know this B, you would have to know something about your UV theory of quantum gravity. Question?
There should be some derivative terms of R as well.
Yeah. So I'm about to say that in a moment. Yeah. Okay. So this is the first higher derivative correction, which is allowed by supersymmetry. The next higher derivative correction, which contributes to this 4-point function, as the audience member was saying, is d to the 4 r⁴. In that case, these general constraints fix it up to 2 numbers. So there's 2 different b's you need to fix. And then you go to the next term, d to the 6 r⁴. Now there's 3 numbers you need to fix, etc. So as you go to higher and higher order, there will be more and more numbers which you need to fix using some theory-specific data in order to know the large n expansion of your 4-point function. A nice aspect of these loop terms is that it was shown in this nice paper by these authors from a few years ago that if you know the tree level terms, then you can use that to kind of bootstrap the loop terms. And this is basically an ADS version of the optical theorem. So you can look at like a unitarity cut, and this gives you a loop from tree level. It doesn't give you the entire one loop term. So it tells you how to get GRR starting from GR, but it doesn't tell you how to get this contact term. So there's always some contact term ambiguities which are not fixed by this method. But these contact term ambiguities only contribute to CFD data of a finite amount of spin, as shown by the classic paper by HPB. Another important aspect of loop level versus tree level is that the calculation of these loop terms, as I will show in detail in a couple of slides, is very sensitive to the KK mode spectrum. And this is unlike tree level supergravity, which does not care about the KK mode spectrum. And so if you want to be sensitive to your compact spacetime factor, you have to go to one loop level. Okay, so let's give an example of this expansion to make it a bit more concrete. So let's consider M theory. So the bulk spacetime dimension is 11. So we can plug in 11 into the formula from the previous slide. And we're going to consider M theory compactified in ADS 4 cross S7 dual to 3D ABG M theory. So in this case, just plugging in D equals 11, we have disconnected term, tree level supergravity, the first higher derivative correction, which is r⁴. In this case, the scaling goes like -5/3. And then this B is the numerical coefficient we want to fix. And then here's the one loop term with its contact term ambiguity. Here's the next higher derivative correction. It goes like C to the -19/9. There's 2 terms we want to fix, etc. for these increasingly higher order terms, including the one loop term now with an r⁴ vertex as well as an r vertex. And so as you see, the higher order you go in this low energy expansion, the more constraints you need in order to fix these coefficients B. But the power of Rastelli and Zhao's, so-called analytic bootstrap is that, a priori, it would have just been a completely general function in each order in 1/C. But after putting in these very general large n and kinematic constraints, now we only have to fix a finite number of numerical coefficients. So it's kind of like at this point, we've kind of taken advantage of all the general kinematic constraints. Now, in principle, all these coefficients B should be fixed by M theory, because if M theory truly is a UV theory complete theory of quantum gravity, then we should just know all the coefficients in flat space, do dimensional reduction, and thus fix all these coefficients in ADS. But We don't know how to do this for two reasons. First of all, we don't know all the higher derivative corrections in flat space. After all, that's what we're trying to solve for. And second of all, it's extremely hard to do dimensional reduction in practice. And so I don't actually know any successful example where people really did proper dimensional reduction. Although there's been some valiant attempts by Arkady-Zeitlin and collaborators. And so instead, the way we've kind of tackled this problem is starting from the CFT perspective, where we use constraints from supersymmetric localization to fix some of these low-lying B coefficients. So in particular, in these various papers with these authors, we managed to fix the B coefficients for the R to the 4 guy, as well as the D to the 4 R to the 4. But we do not yet have enough constraints even to fix D to the 6 R to the 4, which is still protected. And conceptually, we would not expect that a protected input like localization, even in principle, would be enough to fix high derivative corrections that are unprotected, i.e. the D to the 8 R to the 4 and higher. And so if you want to be able to fix D to the 8 R to the 4 and higher, you would need some more powerful constraint rather than just doing an analytic large N expansion plus localization. And I believe that that more powerful constraint is doing the finite N numerical bootstrap, as we'll discuss in a few slides. Okay, so now let me give you yet another example of this large N expansion. Now, where the bulk spacetime dimension is 4 instead of 11. And so we just plug in D equals 4 into our general D expression. And so this corresponds to pure supergravity in AD is 4 with no compact space. And so when we plug in D equals 4, the expansion actually looks much simpler. So just as before, we have disconnected tree level supergravity, and those terms are identical because those terms don't care about the compact spacetime factor. But at one loop, it starts to differ because the one loop calculation is sensitive to the KK mode spectrum. And because we have no compact spacetime, we just don't have any KK modes other than the gravity. So this is a different function, and now it's G tilde instead of G. And then here I show a 2-loop term as well as a 3-loop term. And curiously, the first higher derivative correction just from dimensional analysis first shows up in this order. So it's actually at the same order as the 3-loop guy. And so, to emphasize yet again, it is the 1-loop term which is sensitive to the compact spacetime, not tree level supergravity. And so if we want to differentiate between pure supergravity versus AD is 4 across the 7, we will want to compute this 1-loop term GRR, as we will discuss now in the next slide. Okay, so how exactly does one compute loop from trees? As I hinted that one could do before. And so the basic idea, question?
Yeah, sorry, just conceptual. The pure ADS4 case, there's no dual here. So this
Yeah. So I'm just defining some putative theory I call pure supergravity, and it's defined such that it doesn't have any light single trace operators other than the graviton. And so this is something which I'm defining first just as a low energy effective theory, which is perfectly fine. And then later I will boldly suggest maybe it could be defined non-perturbative. But right now I'm just defining it. And so it would be putatively dual to some exotic CFT. And so the CFT again is just defined as having no light single trace operators other than the graviton supermodels. So it's being defined. So I don't actually know of a microscopic top down construction corresponding to pure supergravity because indeed for many years many smart people have tried to find such an example and they've never been successful. So instead I'm just trying to show evidence that maybe this thing could exist coming from the bootstrap, but I haven't gotten up to the evidence yet.
So this C is again just basically like LADS over L.
Yeah, because C, so the nice thing about just talking about the large C expansion is that C is something which is defined kinematically. It's you don't need some microscopic definition. C is just the inverse of the stress entropy coefficient. And so that exists for any putative C.
This you can do for any amount of Susie.
In principle, this large C expansion you can do for any amount of supersymmetry.
Including 0.
Including 0, yes. Yeah, so I'll talk about 0 at the end of the talk. I'm focusing on maximal supersymmetry simply because that's where things are most constrained, and let's start with the easiest case. Okay. But yeah, indeed, less supersymmetry is interesting, and I'll talk about that. Okay, so now let's talk about one loop from tree level as discussed in this earlier paper. So how does that work? So there's something called the Lorentzian inversion formula, which was discovered a few years ago, and that tells you in general, it's a non-perturbative statement that you can fix the full 4-point function if you know it's double discontinuity in the limit where v goes to 1. So a double discontinuity is something like log squared v, because each log v is a discontinuity, and you have it twice. So now there's a caveat where the Lorentzian inversion formula fixes the 4-point function up the contact terms that contribute to a finite amount of state. So it doesn't fix it fully, it almost fixes. But let's apply this Lorentzian inversion formula in this 1/n expansion. So if you take the block expansion of your 4-point function, and if you just expand the block expansion to 1/c² order, you will see that the only term which has a log squared u term is this term. And so what's special about this term? Well, the coefficients that show up here are all fixed by tree level and generalized free field theory. So in particular, this OP coefficient squared is for the generalized free field theory. That's what the 0 means. And then R means that this is the tree level anomalous dimension. And so even though we're at one loop order, the specific contribution to one loop order is fixed from lower orders. In particular, what is the specific safety data which is contributing? It is these unprotected multiplets, which in this large N expansion, we could think of as double trace operators, which have this scaling dimension, for general space-time dimension. And so why do we care about the log squared U term? Well, the reason is that if we now do crossing, this makes U into V. And so this is now the only contribution of log squared V, i.e. this is the only contribution at one loop order, which actually contributes to the double discontinuity. And so now you see why you can get one loop tree level, because the only thing which contributes to the double discontinuity at one loop is this term, which can be completely fixed from tree level and generalized free field. And so that's kind of the clever argument came upon by those authors. And that's how we compute one loop in practice. Now, it's difficult to actually do this in practice due to mixing. And this is where the sensitivity to the KK mode spectrum comes into play. So the KK modes that we have for some ADST plus 1 bulk are dual to single trace operators, which I denote as SP for P greater than or equal to 2. So this is the scaling dimension, P times E minus 2 over 2. So for instance, when P equals 2, this is the stress tensor, which I called just S before. But of course, you have this in general for higher. So in particular, if we're doing ADSD plus 1 cross S, so if we have like a bulk compact factor that's a sphere, then we would have KK modes for all integer P. If the bulk is a sphere mod Z2, which also preserves maximal supersymmetry, then you would only have single trace operators of even P. And then finally, if we don't have a compact spacetime factor at all, which is how I define pure ADS, then we only have P equals 2. So we only have the stress tensor, i.e. we only have the gravity. So now let's look at the double trace operators which contribute this, this one loop double discontinuity. So we write them as 2 single traces, SD and SB, and then we dress them with derivatives. So L derivatives for spin L, and then we can put N boxes. And so as you can immediately notice in this large N limit, there are going to be many operators which have the same dimension, because different combinations of P and N will add up to the same scaling. And so this is kind of the degeneracy issue. And so when we want to compute this quantity on the previous slide, this is really an average of the degenerate double trace operators weighted by their OP. And so if we want to compute this average, we have to compute not just the stress tensor 4-point function at tree level and generalized free field theory order, but also you have to compute these other 4-point functions of these other single trace operators at tree level and at GFFT order. But we can do that, and then using this data, we can then do this unmixing and thereby compute the one loop double discontinuity, i.e. the full one loop correlator up to contact. And so that's really where the difficulty of this calculation lies. So it's very hard to do this unmixing in practice, but with a lot of hard work, it's successfully been done in every single case. So here I'm just going to do a brief literature overview of all the cases that were worked out. So people originally did this unmixing in 4D maximal supersymmetry in the ADS5 crosses 5 case in this very nice papers. This was then generalized to the case with the mod Z2 overfold, which also has maximal supersymmetry. In this context, recall that this method fixes your one loop guy up to a contact term. And to fix that contact term, you have to know some theory specific data. And so in a paper I wrote a few years ago, I used localization to fix that contact term, and I found that it was non-zero. Precise value is not so important. So this one loop from tree level was also done for 3D maximal supersymmetry, both for ADS4 crosses 7, as well as ADS4 crosses 7 mod Z2. The calculation was much harder for various technical reasons. And kind of a curious fact is that in this 3D context, it turns out that this contact term could be shown by localization to be 0, which I think might be related to the fact that the bulk dimension is 1. That's kind of a curiosity. And then finally, this calculation was also done in 60 for both ADS7 crosses 4 mod Z2 as well as ADS7 crosses 4. And in this case, we don't have localization, so we don't know the value of the contact, but maybe it's also. And then finally, in my recent paper with Fernando, we also did this one loop calculation for this putative pure supergravity theory. And so this is actually a much easier calculation than the previous ones because the KK mode spectrum is basically trivial in this case. And so the point of this slide is just to show you that the one loop correction has been computed for all the relevant cases. So all the cases of maximal supersymmetry. And so we have something to compare to at one loop. Okay, so.
Sorry,
Yes.
what was the logic that no contact terms since bulk?
Okay, okay, good question. So basically, the logic is that you have a contact term, kind of as shown in this previous slide, if there is an R to the 4 term, which shows up at an order lower than the one loop term. And so, you know, when the bulk dimension is big, like 11, then you'll always have such a term. When the bulk dimension is small, then you see that like the contact term shows up at a much higher order.
So it's just some dimensional reason.
Yeah, it's dimensional reason. It's another way of saying that, like, you know, you could ask a question of like, is one loop for graviton scattering finite or not at a certain moment? And so it turns out that the one loop diagram for graviton scattering happens to be finite when the bulk dimension is small and it starts to diverge once the bulk dimension gets big. So that's kind of like a general, you know, general known fact. Go back to the 70s. Okay, yeah. Thanks for asking that question. Okay, so now we're going to transition from large n to finite n. So now we're talking about general finite n constraints applying to any theory. We don't make any assumption about the theory at all. So this numerical bootstrap bounds we can compute for any max supersymmetric CFT. It's a function of C. And what it gives us is non-perturbative upper bounds on scaling dimension of unprotected multiples. We can also get both upper and lower bounds, i.e. islands, in the space of OP coefficient squared of certain multiplets. Or in particular, we can get the upper bounds in general, and we can only get the lower bounds if this the protected multiplet we look at is separated from the continuum of unprotected multiples. And so for each case, I will say whether or not this is true or not. The most important aspect of these bootstrap bounds, which everyone should really be aware of, even if you don't know all the technical details, is that these bounds are proved monotonically as a function of the truncation of the crossing equations. So like we start with an infinite set of crossing equations, and if we want to put this on a computer, we have to truncate them. So let's parameterize that truncation by something I call capital lambda. And the point is that as you increase these lambda, the bounds always get better and better and better. And this is what makes the numerical bootstrap rigorous. Because if the bounds were just kind of fluctuating, then we would have no expectation that the bounds would always get better. And this is one of the big advantages that numerical bootstrap has over other numerical non-perturbative methods, say such as like lattice, where it's like when you're studying things on the lattice, it's not 100% that as you increase like the lattice spacing or the volume, that like things will always change in one direction. And so like another way of saying it is that each bootstrap bound is like a mathematical theorem. It's a mathematical theorem with a messy origin, but it's a rigorous theorem nonetheless. Okay, so now I'm going to go through case by case for every maximally supersymmetric dimension, showing the bootstrap bounds and how they compare to the one loop analytic prediction. So let's start with 4D, which is the case people are probably most familiar with. So what do we know about maximally supersymmetric CFTs in 4 dimensions? So all the theories we know of are described by Mills, which is defined by its gauge group, which is some classical Lie group, as well as the complexified coupling tau, which is just Mills adding the theta. So when the gauge group is SUN, then this is dual to type IIB string theory on 85 process 5. And when the gauge group is SON or USV2N, then it's string theory on 85 process 5 mod Z2. And so these are the 2 cases we know about. I'm not going to consider the exceptional groups because those don't have a large number. So the way we relate this to the bulk is using the standard ACFT dictionary. So in particular, n is proportional to this power of string length, where this O is just either 1 or 2, depending on if you have an orbifold or not. The other aspect of the mapping is that the complexified coupling in the gauge theory, tau, is just the complexified coupling in the string theory, tau string. So in addition to these known n=4 CFTs, we're also going to discuss this conjectured exotic CFT, which is whatever CFT is dual to pure 85 supergravity. So this is some CFT which has a light single trace spectrum by definition with only the graviton. And it also has some conformal manifold because every maximally supersymmetric CFT in 4D is a conformal manifold, but we don't know anything about its conformal manifold. I guess the one thing we do know is that it doesn't have a weak coupling limit. Because if it had a weak coupling limit, I believe there are theorems proving it has to be n=4 superunits. So this doesn't have a weak coupling. Okay, so what are the kinematics of the stress tensor 4-point function? So the only non-trivial multiplet in this OPE is the singlet long multiplet. Everything else which appears is totally trivial because all the various short multiplets are just completely fixed by the free theory. So there's only one guy we care about. And so let's show the bounds on the scaling dimension of this unprotected multiplet. So this is the first plot. So even if you weren't following all the technical stuff before, hopefully you can wake up and look at this plot because this is one of the main results of today's talk. So on the x-axis of this plot, we have 1/c. And so we're looking in the large C regime, i.e. the large N regime. So this is like C goes to infinity, which is disconnected, and then this is going to like more and more, less geometric as we go to finite C. The y-axis is the scaling dimension of the lowest dimension operator of spin 2, which is unprotected. Which is just an example of CFD data we're going to look at a bound. So at C goes to infinity, we know just from the generalized free field theory, that's dimension 6. And the interesting thing is what happens as we go to finite C. So the black line is this upper bound that we get from the numerical bootstrap. So the bootstrap is telling you that any theory with maximal supersymmetry must be at this black line or lower in this lightly blue shaded region. It's a little bit hard to see on the projector. And so black is non-perturbative in C. These other colored lines are then comparisons to the 1/C expansion, which we did for each specific theory in the previous part. So we start with the leading 1/C correction, which is tree level supergravity. That is not sensitive to the spacetime factor. That's this gray dotted line. So at very, very large C, the gray dotted line is right along the bootstrap bound. And that itself is interesting. And that's suggesting that this bootstrap bound, even though we're just looking at one specific 4-point function, seems to be, kind of maximally constraining in that the expected 1/C correction is right along the bound. But of course, as we go to finite C, this is just the 1/C approximation, so we don't expect it to still remain good. And so indeed, as you go to finite C, you start seeing that this 1/C correction just goes somewhere within the allowed region. But now let's see once we add the 1/C squared correction, one loop correction. So that should improve our large C approximation. And so when we add the 1/C squared correction for ADS 5 crosses 5 mod 2 or ADS 5 crosses 5, which are the two known CFTs, this N equals 4 super N mils, then we find that it actually pushes the tree level approximation in the wrong direction because these corrections are negative. Whereas
In what sense is it wrong?
Sorry?
In what sense is it wrong? It's loud, right?
It's allowed. I'm not saying it's wrong. I'm just saying that it's pushing it away from the numerical bootstrap. So it's pushing it away from the bound.
It's not saturating the bound.
Not saturating the bound. Yeah. So you
Are
see
you
that.
at a specific coupling when you're talking about those?
No, okay, that's a good question. So this bootstrap bound should apply to any value of the coupling. Because we aren't sensitive to the value of coupling. We don't know how to put it into the bootstrap. So the only thing we're putting in is the value of N, i.e. the value of C. But we're agnostic about the conformal map. That's a good point. And that's a point I'll talk about in the next couple of slides. So you see that the one loop correction for these guys is just pushing it somewhere into the allowed region. So no longer saturated. But very curiously, when we add the 1/C squared correction for pure ADS 5, that has the right sign and even the right magnitude to continue non-trivially saturating the bound for an even larger range of C. And so you can see that this dotted orange line is almost exactly on the numerical black line, for this fairly large regime of C. And so again, this is not trivial. First of all, it had the right sign. Second of all, it even seems to have the right magnitude. Now, of course, question?
Yeah, following up on Clay's question, so if you're agnostic about the coupling constant,
Yes.
like that those lines corresponding to ADS 5 cross S5 or whatever, they could fluctuate.
No, but the thing is that at one loop, the one loop correction is also not sensitive to the coupling. So when you do this large N expansion, the terms that are sensitive to the coupling would be kind of like higher derivative corrections. The one loop correction is supergravity squared is not sensitive to the coupling for the same reason that tree level supergravity is not sensitive to the coupling. So the Einstein-Hilbert vertex is not sensitive to the coupling, nor the 4 vertex would be, but not this guy. Yeah. So that's a good point, and this is also why we can avoid the subtlety of coupling dependence. So at least at this order, in principle, this 1/C squared should be a reasonably good approximation, and we find that the one that saturates the bound the best is pure ADS. So this is really one of the main thoughts in this talk. So let me know if you have any further questions. And I'll let it sink in. Yeah, question?
What kind of precision are you working with to convince yourself that it's really inside rather than outside?
Excellent question. So we are doing bootstrap precision, capital N equals 123. That is an extremely large amount of precision. So to give you some perspective, this is many orders of magnitude more precise than Rosselli et al.'s original study in 2013. And we pushed it to this enormous precision so that we could be very, very satisfied that this bootstrap bound was not going to change anything. So at least at the level of visually looking at this plot, I promise you this black line will not change as you go to higher precision. It took us, for instance, 2 weeks on a supercomputing cluster with 40 cores running simultaneously to get this plot. And so in particular, we did many specific values and then we did a fit, and that's what gives us this plot. Okay. So now let's address this question of the coupling dependence. Because of course we know that every 40 CFT should depend on the coupling. So for the most general bootstrap bound, we don't know how to put in the coupling. But now let's specify to specific theories by putting in non-perturbative data that we know about specific theories. And so the only non-perturbative constraint that I know about is localization. I mean, even integrability only works at large. And so in this series of papers with Silviu, we derived two exact relationships between the derivatives of the massive form free energy and a certain integral of the 4-point function. And this massive form free energy can be computed exactly at finite n and finite coupling. And so here in these plots, we specified n equals 2 for super Yang-Mills. And now that we can put in this non-perturbative thing that depends on tau, we can get bounds that depend on tau. And so in this plot, I showed these improved bootstrap bounds, specifically for SU2 super Yang-Mills. So the orange is the new allowed region. This is to be contrasted with this gray dotted line, which is the bound you would have gotten from the previous slide if you didn't know the localization bound. So of course, this is a horizontal line because the old bound didn't depend on G-angles. Only the new bound does. And so there's several interesting things about this new improved bound specifically for SU2 super Yang-Mills. First of all, if we can look at the regime of weak coupling, where we can compare two predictions for, so here we're plotting the lowest dimension singlet. This is what's called the Konishi of weak coupling. This thing has been computed to 4 loops in a small Yang-Mills expansion. And rather remarkably, we find that this perturbative weak coupling calculation exactly saturates our bound for a pretty good regime of Yang-Mills in the free theory regime. And so this is really remarkable. And to me, I think this gives strong evidence to believe that this upper bound in general, even in the strong coupling regime, is likely approximately corresponding to the physical SU2 super Yang-Mills theory. So I just want to emphasize that, this is, I think, a very exciting result, because I think this is really a first step towards exactly solving n equals 4 super Yang-Mills at finite coupling and finite n. Now, of course, we've only done n equals 2. We also did n equals 3 in that paper. But in principle, there's nothing really stopping us from doing more values of it. And that's something we're working on at the moment. And so here in this plot, you see I'm just plotting Yang-Mills. I'm not showing the theta dependence. The theta dependence is actually very weak in this regime of Yang-Mills. And so to kind of show you how weak the theta dependence is, here I let tau go from I to e to the I pi over 3. So, and we're looking along, a certain slice of theta, a certain slice of tau. And you see that the dependence on the theta angle is very weak. So it's only changing, like the third decimal. And maybe this would match your intuition because the theta dependence comes from instanton corrections to this free energy. And I guess instantons turn out to be very weak. Now at large n, we knew they'd be weak, but it turns out even for the smallest value of n, i.e. n equals 2, they're also very weak. And so, another kind of curious fact about this is that the biggest value of the bound occurs at e to the I pi over 3. And there's kind of 2 special points on your conformal manifold. There's tau equals I and tau equals e to the pi over 3. One has Z2 enhanced symmetry, one has Z3 enhanced symmetry. And so it seems like the Z3 enhanced symmetry point, which is this point, I guess seems to be the point with like the biggest value of this Konishi algorithm. That's kind of another interesting thing we learned from this plot. But for the purpose of this talk, the most interesting aspect of this plot is the fact that there is a gap between the biggest value of the upper bound improved with localization versus the most general upper bound. And so what does that gap mean? That means that there was no value of tau in the conformal manifold for super Yang-Mills, which could possibly have corresponded to the most general bootstrap bound. And so in the previous slide, I showed you evidence that in the large n regime, the thing that was saturating the most general bound was not super Yang-Mills, it was instead this exotic pure ADS4 supergravity theory. Now I'm showing you in the opposite regime of the smallest value of n, there too, we have proof that the theory that's saturating the bound cannot be super Yang-Mills. So of course, in this very strongly coupled regime, I don't really have any data for pure supergravity to compare it to. But considering that at large n, it's saturated by pure supergravity, and at finite n, it can't be saturated by pure super Yang-Mills, this hints to the fact that perhaps there is some non-perturbative version of pure ADS4 supergravity, which continues to saturate this gray line.
There, how do you know for larger n, it doesn't move up?
Well, it would gradually move up, but we know that it's sufficiently large and it's also not saturating the bound from this point.
But sorry, that was a bound that was supposed to.
So like this is large n,
Right.
this is finite n. And so,
You say therefore it means there's no value of the coupling for any SUN that can.
yes, for any SUN or SO.
Is that logical? Can it go like saturate some n equals 100?
Sorry.
Is it possible that
Yeah,
that's saturated at the SU 100 logically? Just asking.
No, but I know, but we already know that can't be the case from this plot.
But
Because then this plot applies to any maximally supersymmetric CFD
But
for any
only an
value of tau.
infinite n limit. I think Kentaro's point was maybe it kisses the next plot for SU100 and then goes back down to that.
Okay, sure, yeah, so I agree, yeah, there is a logical possibility that it could be for some large or finite value of n, it could maybe kiss it and then go back. Yeah, so that's, I guess, a loophole we haven't ruled out, although I think it's extremely unlikely. But indeed, it would be good to close that loop. Yeah, thanks for the clarification. Okay, so this is an example of this kind of curious hint that perhaps this pure radius force of gravity might mean something even at finite n, which is very surprising. Okay, so this concludes my discussion of 4D. And now let's move on to the other cases of maximal supersymmetry. So now let's talk about 3D maximally supersymmetric CFTs. So again, let's discuss the known theories. The known theories are Chern-Simons-Mander theories with two gauge groups, Chern-Simons coupling K, and gauge groups N for one, N plus M for the other. These are called ABJ theories, after the authors. Now, because we want to look at maximal supersymmetry, this restricts the allowed ranks to the Chern-Simons level could just be 1 or 2, and the difference between the gauge groups can only also be 1 or 2.
You're talking about the known ones that have an infinite n limit. There are also some sporadic known.
Sure, yeah. There's also these BLG theories. I'm only talking about stuff that have large n. This is also why I didn't discuss exception.
Yeah, but I think as compared to 4D, in 3D, there's not even a kind of guess as to what the list of maximally supersymmetric.
Well, yeah, there's the ones that are known, but it could be that there are other ones we haven't found yet.
Right, but in contrast to 4D, where at least if you start with some Lagrangian, I think we kind of think we have a list.
Indeed, yeah. The classification is more mysterious in 3D than despite many years of looking for such theories. So we're focusing on maximal supersymmetry. So in maximal supersymmetry, the large n dual is always going to be M theory. So in particular, a large n at fixed K, we have 80 square cross 7 mod CK has the ADCFT dictionary where 11-dimensional Planck length is related to this power of C, addressed by the factor of K. Just following from dimensional analysis. Now, just for generality, I'm going to note there are other limits which don't have maximal supersymmetry, but just for generality, one could also consider the large n and large K limit with fixed ratio. This would then be dual to type 2A string theory with the following ADCFT dictionary. And there's even another limit where you basically make one of these gauge groups big, and you keep the other gauge group small, and you make the Chern-Simons level also big, and then this is related to higher spin gravity. But just to re-emphasize, this higher spin gravity limit as well as the type 2A limit don't preserve maximal supersymmetry, and so for the purpose of this talk, we don't care. And then lastly, we can just propose this exotic pure radius force supergravity. So this is the list of CFTs we're going to look at. So what are the operators that can appear in this OP? So similar to 4D, you have long multiplets for every even spin. But in addition to what we had in 4D, we also have short multiplets, which are non-trivial in the sense that their OP coefficients aren't just fixed by the free theory. And so the list of protected guys that we're going to look at are multiplets called B and multiplets called A. So the B multiplets have spin 0, whereas the A multiplets can have every either even or odd spin. And so these guys, their dimension is fixed, but their OP coefficient is non-trivial. And we can compute both upper and lower bounds on these B's and A's because they are separated from the continuum of long operators. So now let's show the results from numerical bootstrap. So here I'm going to show two plots, one for a scaling dimension of an unprotected guy and one for an OP coefficient of a semi-short guy. So this thing is a little bit more protected, so the plot looks a little bit nicer. So let's start with this plot. So again, we're looking at the large C regime, which is why we're looking at 16 over C, going from the generalized free field theory down to strongly coupled. Here is the upper and lower bound on the OP coefficient. So black is upper bound, this is lower bound. And so in the very large C regime, we see that this gray line, which is
So why do we have upper and lower bound?
because so as mentioned, you can get both an upper and lower bound for OP coefficients of protected operators if their scaling dimension is separated from the continuum of long. So this is something you can do in 3D, you couldn't do in 4D. And so it turns out that the interesting bound happens to be the lower bound. And so you see that this tree level guy saturates the lower bound at very large C. As you get to more finite C, it starts to differ. Now let's put in the 1 over C squared correction. For 80 squared across 7, it's across the 7 and mod Z2, which correspond to the two ABGM theories. That just pushes it in the wrong direction. Whereas for the pure ADS4 guy, that pushes this tree level correction to be exactly lying along the bootstrap. So again, we find the same pattern that we found in 4D, which is that the one loop correction coming from pure supergravity makes it so that your 1 over C expansion is exactly saturating the bound, whereas the one loop correction coming from duals of known theories is just somewhere in the allowed range.
Sorry, so the just maybe it's a numerical thing, but
Yeah.
the the right-hand side of this plot, the purple seems to intersect the upper bound.
Yeah, this doesn't really mean anything. I mean, because I mean, after all, like this is just, we're just doing 1 over C to some finite order. And so like, once you look at very finite C, I mean, these expansions would be really bad. And so,
But wouldn't you say the same thing about the coincidence that you were telling us at the bottom? Then?
yeah. So look, it's always an art to say like, what is the regime of C for which we should trust this 1 over C expansion? And so I can just, it's just suggestive that there is some regime of large but finite C where it seems that this one loop correction for period D4 seems to be a pretty good correction, considering that it continues to saturate the band. Now, as we go to more and more finite C, presumably, you would need to add more terms in the 1 over C expansion for it to continue to be a good expansion. But whenever you're comparing perturbative data to something not perturbative, there's always going to be, to some extent, an art of the regime in which you trust this.
But the left-hand side one seems to be excluded.
So this plot, yeah. Okay, so in this plot is just a little bit harder to look at because it seems that the 1 over C expansion is worse. We could just clearly see that. So like 3 level only works for super large C, and then the 1 loop correction for the known ABGM guys is really bad. It already diverges very early C. But even in this plot, there is like a larger range of C for which adding the 1 loop correction for the period DS4 it actually seems to improve. So it's a smaller range of C. Why that's true, I don't know. I mean, again, you're comparing perturbative data to non-perturbative data, but I would say there's like a reasonable range of C, maybe from C equals infinity all the way up to C equals 0.04, where it's noticeable that adding this 1 loop correction improves the tree level supergravity to continue to saturate the bound. But it is a little bit harder to see from this data versus this data. But I would still say that in general, we see a pattern similar to 4D, which is that the guy which is closest to saturating the bound for some reasonable range of C is the pure supergravity guy, not the one that's dual to known theories like ABG. Okay, so in the 4D case, remember we also showed improved bounds upon putting in data specific to the theory from localization. So we can do something analogous in 3D. So in 3D, the thing we know from localization is the value of the OP coefficient of this short operator B. So here's a plot showing upper and lower bounds for this short operator B. So the black line is the upper and lower bound. The dotted line is just the upper and lower bound with lower precision, but let's forget about that. And then these colored lines are showing known maximally supersymmetric theories. So the blue values is for something called BLG theory. That doesn't have a large end limit, so we don't really care about it so much, and it's just somewhere in the allowed region. The ones we care about more are the red and green and purple lines, as well as gray. And the important takeaway lesson from this plot is that all the known theories don't lie exactly along the lower bound. So at very very large C, they're going to be approximately on the lower bound. But once we get to finite C, they're all within the allowed region. And this is analogous to what we saw in 4D, which is that like known theories with known M theory or string theory duals don't saturate the bound at finite N. Instead, they're somewhere within the allowed region.
So actually, can you go back to the 4D plot now? I'm wondering
Sure.
about the quantization of C,
Okay, so let's go back this plot.
the one before.
One before, yeah.
So in even dimensional CFT maximal supersymmetries, C would be quantized by the 't Hooft anomaly coefficients for the R current.
I mean, yes. So I mean, C for any physical theory is always going to have to be some specific value. It can't just be any random value. I mean, so it's proportional to n squared. So in particular, in 4D is proportional to like the size of
coefficient with the,
yeah.
but it's not only that. I mean, and you might say, okay, maybe it's related to SUN, but
Yeah.
but it's also there's a linear relation between that and the R symmetry anomalies, which are quantized.
Yeah.
So
No, it is quantized. Yeah, the value of C for a known theory is quantized.
no, just
Yeah.
not even for also for an unknown theory is also quantized.
Even for an unknown theory to be quantized.
And I'm just wondering if that actually truncates how far to the right you would even ever need to consider this plot.
Okay, so yeah, so you're basically asking the question of like, what is the lowest value of C corresponding to known theory? So we even know what the lowest value of C is because Bootstrap basically says that the lowest value of C is the value of C known for the SU2 theory. So something like C equals 3/4.
And
Yeah.
my memory is that value is not just the lowest value for a known theory, but it's the
Even for
lowest
unknown
value
theory.
for
Yeah,
any.
this is true. Yeah, so but that's more to the right of what I'm showing. So yes, that's a good question. It's like C equals 3/4, and that's more to the right. So in the 3D case, indeed, we also have a general bound on possible values of C, and that's basically this is the free theory, C equals 16, and then the lowest known interacting theory that we know about is this ABJ1 theory, which has the value of 16 over C given right there.
But by contrast, in
Yeah.
3D, there's no a priori theorem saying how low it can go, I think.
Yeah, there's no a priori theorem in 3D. But the main purpose of this plot was just to convince you that even at finite n, i.e. finite c, it seems that known theories are not saturating the bound, analogous to what we found in 3D. And thus suggesting that perhaps this pure supergravity theory is the thing which is saturating the bound, even at finite n. And that's basically what this plot's also telling you. So here's like yet another plot, this time coming from mixed correlators. This black is the upper bound now on the certain scaling dimension. Red is just the tree level correction. This is basically where the free theory would be all the way over there. Here it kind of goes to 0 at this value of 0.7, which is the same value on the previous plot where this thing went to 0. But here again, we see that, this is basically just saying that like this kink here doesn't seem to correspond to any known theory. Okay, so what happens if we, give up on discussing the most general class of theories, but really just try to focus on known theories by doing the bootstrap and putting in the value of localization? The previous plot is we were just comparing most general to localization, but let's put in localization and bound other data. And so that's what goes on in this plot. So forget about the vertical lines. Vertical lines are just telling you where various known theories lie for their value of C. Let's forget about that. So, and let's go through slowly because there's a lot of data in this plot. So the gray upper and lower bounds here and there are the original bounds you got before you put in the value of localization. But now let's put in the localization value for specifically ABGM with k equals 2. So after you put in those known localization values, it improves the bounds quite strongly. So this upper bound goes all the way down to this black line, and this lower bound moves up a little bit to that black line. And what's curious is that this improved plot, which is specific to ABGM with k equals 2, now it seems to match in this large C regime the one loop correction for k equals 2 ABGM. So in this plot, tree level was kind of this dotted red line. And as you see in this range of C, it's kind of diverging from the lower bound. But then once you add the one loop correction for ABGM with k equals 2, it moves it up such that it's now being very close to the bootstrap bound improved by localization. And so this gives us some hope. We're not there yet, but it gives us some hope that perhaps by including more localization constraints, we could just do some numerical fit of this lower bound, declaring that that is what corresponds to ABGM theory, and thereby read off further higher derivative corrections beyond the protected ones. So in particular, we could imagine doing some kind of large C expansion, doing a fit order C to the minus 19/9, and then like looking at the coefficient we get and declaring that as the coefficient of D to the 8 order. So that's something we haven't done yet. But the progress is that at least so far, it seems that at one loop order, we get kind of an approximate match between analytic prediction as well as lower bound. The reason why this is nice is that as far as I understand, this is the only way, even in principle, we'll ever be able to learn about these unprotected high derivative corrections, i.e. this is the only way we'll ever be able to learn about true, M theory S matrix solve orders. Because we just don't have any other known method of going beyond the protected.
You don't think that you could take the expansion in M theory, sorry. You said.
Yeah.
Okay.
For string theory finding coupling would be analogous to that question.
But you'll always have like the window, presumably M theory has
So
a specific.
So right now we kind of conjecture that the lower bound of this lab region is probably what's corresponding, based on the fact that it's matching. It would also be nice to indeed make the window between the upper and lower bound even smaller. It's pretty small already, but there are further localization constraints we haven't yet input, and hopefully after putting them in, that window itself will shrink, so then it should be a totally rigorous prediction. So that concludes 3D. So now we'll move on to the last case of 60. So in 60, all the known theories are classified by these Lie groups. So you have SUN and you have SO2N and then the exceptional group, but the only thing with a large N limit is SON and SU. So we'll focus on those. These are called the A and D series. Now these are not gauge theories because they don't have Lagrangians because we're in 60. Nonetheless, they're classified by Lie groups. So the AN theory is dual to M theory and 87 crosses 4, and the DN theory is dual to 87 crosses 4 mod ZG. So it's always the same pattern. That those are the two cases with maximal supersymmetry. We have the relationship between Planck length and C. And then finally, we also consider this putative exotic C of T dual to pure 87 supergravity. So what are the operators we can look at in this 4-point function? So as in 3D and 4D, we have long multiplets for every even spin. As in 3D, we have some short multiplets whose scaling dimension is fixed, but whose OP coefficient is non-trivial, which we can bound. But specifically in 60, unlike 3D, it turns out that these protected guys actually abut the continuum of long multiplets. So that means we can only compute upper bounds for these guys. We can't also get lower bounds. Another interesting fact about 60 is that the free multiplet appears explicitly and it's separated from the continuum of operators. We can kinematically restrict to interacting C. So now let's show the plots in this case. So just like in 3D, we're going to show a plot on a certain scaling dimension. as well as a certain semi-short OB. So these 6D plots, they're a little bit harder to see visually than 3D and 4D, which is why I showed them last. And so in this case, the x-axis, I'm actually looking at the entire range of C, which is even allowed. Because this value of 0.04 is actually the lowest known value of C. So this is the value of C for the A1 theory. And so it turns out that the CFT data depends weaker on C and 6D than it did in 3D and 4D. And so, related to that fact is that it seems that the one loop correction actually seems to be pretty good. Because, here is the gray line, starting C on this plot, matches the upper bound at very large values of C and more finite values of C, it diverges. And then, but once you put in the one loop correction, the difference in one loop corrections for these various theories is very, very small. So as you can see, you can kind of barely see. And this is why I'm showing the plot last. So like this result is consistent with my conjecture that the pure ADS sky is saturating the upper bound, but the evidence in 60 is weaker than the other cases, simply because the difference between these corrections are very small. Now, I can tell you analytically that, you could just compare the exact value of the one loop correction, and it is true that the value of the pure ADS 7 guy is closer, it's less negative than the rest of the guys. And so, it has to be closer to this bound than the other guys. Nonetheless, it's a bit hard to see visually. For this CFT data, you can see it a little bit better, where you can see that there's like a notable difference between purple for 87 crosses 4 as well as orange. So again, orange is negative, but with a smaller magnitude than 87 crosses 4. So it's closer to the numerical bootstrap bound. So one kind of curious fact. So in Rosselli's original paper from 2015, they computed some bounds on the allowed value of C for any interacting theory, which you could do because this free multiplet, you can just kill it, and so you can only look at interacting theories and then just do a general bound. And so here in this plot, the x-axis is how precise the bootstrap is, because lambda is your precision parameter. So it's getting more precise as you go closer to 0.
I really don't understand. You can the minimum allowed value
Yes.
is quantized and known.
Well, no, it's not known. It's like people, okay, for theories that we know of, we know allowed values of C. But like this is supposed to be a general lower bound
No, but
for any theory of maximal supersymmetry.
No, but a priori, the anomaly supermultiplet
Yes.
fixes the value of C
Sure.
in terms of the R current anomaly.
Sure. But you have to know what that anomaly is.
No, but all known values are saturated, and that R current anomaly is also quantized. So it cannot vary continuously.
Sure, but is this something you know for any 60 maximal supersymmetric
Yeah.
CFC? You're saying like,
Let's do it kinematic.
okay, so okay, fine. So yeah, so perhaps okay, maybe look, this is not my plot, this is their plot, so maybe you'd argue it's not that interesting. But like what they were trying to claim from this plot is that maybe this is true, based on anomaly considerations. They were trying to claim that just from doing crossing symmetry, i.e. bootstrap, and some kind of infinite precision limit, the lower bound on C would roughly converge to the lowest known value, which is C equals 25 for the A1 theory. And so like the reason why they cared about this thing, being saturated is that when a theory saturates the bounds, it's interesting because then you can in principle read off the rest of the CFT data from the crossing equations. And so they would want to claim an infinite precision limit, specifically for the A1 theory, that would be the thing saturating the bound, and thus you'd be able to read off its data. And so this would have some tension with my conjecture, which is the thing that always saturates bounds are not known theories. Instead, it's this exotic 87. But my objection to their claim is that this required some unjustified extrapolation. So they weren't able to go to infinite precision. The bootstrap converges very slowly in 6D. There's no reason to believe that the dependence on this bootstrap parameter lambda is linear. This is just some random human parameter. And so I think it was a very bold conjecture to extrapolate from there to there. And so, it could well be the case that really it's like 20 billions. It would have to allow 25. But I think it's a little bit too bold to claim that it's exactly 25. Because instead, I would like to think that the theory which is saturating the bound is never one of these known, A or D series theories.
Well, I think you would have to capitulate though that it has the same values as their C's, because those values are a priori quantized and known.
Sure, okay. That could be an alternate interpretation, is that there could be maybe two theories of the same value of C. One of them being the physical theory, one of them being this exotic CFT, and they happen to coincide for lower values, for higher values. Yeah. There could be some different sequences.
We can talk, maybe let's finish and then we can talk about it.
Okay, so in conclusion, so what did we discuss in this talk? So we discussed large C expansion holographic correlators. First, we discussed how you could fix this analytically at large C in terms of a few coefficients. And then in particular, we fix them up to one loop order just based on the KK spectrum. Then we compared this to general non-perturbative bounds for maximally supersymmetric CFTs, dual to ADS-T plus 1. And we found that the non-perturbative bounds were saturated in this large C regime, not by the guys you would have expected, which is the known theories, dual to string theory and M theory, with ADS cross S, but instead the thing which was saturating these bounds was these weird exotic pure supergravity theories, which have no compact factor. And then we showed some intriguing evidence that even at finite C, where we don't really have a microscopic definition of these theories, nonetheless, we know that the thing saturating the bound could not be the known string M theory tools. It has to be something else, perhaps a non-perturbative version of the pure supergravity theory. As a side point, we also showed that once you put in data that we know about n equals 4 or ABGM, so put i.e. localization data, we could then improve the numerical bootstrap bounds. And we even have some evidence that these improved bounds might be non-perturbatively solving the theory. So we are kind of like, very close to having a non-perturbative solution to n equals 4 Sprague Mills and ABGM. And that's interesting because that in principle could be used to read off higher derivative corrections at d to the 8 to the 4 order and beyond. Thus, solving the S matrix for these. So that, of course, is one of the future directions we want to do. We want to improve the precision of these bounds, put in more localization constraints. In particular, there's constraints due to derivatives of the squash sphere we haven't considered yet, which would probably improve our bounds. So our specific goal is to get d to the 8 to the 4. That's the first unknown guy. In the 6D case, we don't have localization. We actually have something analogous to localization. So there's something called the 2D chiral algebra. This describes a certain protected subsector of the theory. And this chiral algebra is a non-trivial thing. So for like the A theories, it's specific W infinity algebra, and that gives non-trivial predictions for certain OB coefficients as a non-trivial function of C. And so we know what those are. That was worked out in my paper with Eric from 2018. And so it'd be nice to put in those values and thereby, kill this exotic theory and instead focus on the A series. Going back to the main theme of comparing, pure supergravity to these bounds, it would be nice just to compute the 1 over C expansion to higher order. Because so far we computed to order 1 over C squared, we computed to 1 loop order, but it would be even nicer to compute it to 2 loop order, because then presumably we would then be able to compare the 1 over C expansion to some bigger regime of C. So for instance, in one of the 3D plots, you saw that it seems like you'd only really trust the large C expansion to some fairly small regime of C. And so to give us more confidence that we're really seeing saturation, we should compute the next order and see if it improves the match. So if the match gets worse, then probably that's evidence against my conjecture. But if the match gets better, then I'd be very happy. And I think it's actually quite feasible to do this calculation in 2 loops for the pure theory. Now, for the physical theories with a compact spacetime factor, that's super hard. But for the pure theory, I think it's quite feasible. There was a nice paper by Vafa et al., which inspired by our work, which said how if this pure supergravity theory existed, then this would contradict some of the dogma of the swampland program. Because it is a cherished belief of swampland people that you cannot have a theory of quantum gravity which has a global symmetry in flat space. And now if you have this pure supergravity theory on ADS, you could simply just take the flat space limit, and that would give you a theory of pure quantum gravity which has a global symmetry. Why? Just the R symmetry. So in the case where you have ADS cross S, when you take the flat space limit, you no longer have a global symmetry because the R symmetry gets geometrized. So for instance, when you have ADS 5 crosses 5, you have an SU4R symmetry, but in the flat space limit, you get 10 dimensions, and then this R symmetry just becomes the isometries of the extra 5 dimensions. But if you're really looking at pure ADS 5, there's no extra dimensions to soak up the R symmetry. So you just have pure quantum gravity with a global symmetry left. And so, that's a very
Why is it gauged? I don't understand that argument. Why wouldn't it also be gauged?
because you don't have extra dimensions to geometrize. I mean, you would use
In
So it's
ADS
a global
DFT,
symmetry.
wouldn't the bulk global symmetry, whether or not it's geometrized, would always be a gauge symmetry in the bulk.
But that's only the case you have gauge supergravity. It's like the
No, that's
theory.
part of the ADS CFT dictionary, I thought, that any global symmetry.
No, but that's on ADS. The idea is that we're taking the limit as ADS goes to infinity, but you go to flat space. So the statement is that if you start with the theory on ADS, and if your bulk space-time dimension is
So
ADS.
in ADS, let me make sure I understand. In ADS, you say it is gauged,
What's gauged?
the R symmetry,
In ADS within the bulk, it's gauged, yes.
okay? So how does that not continue to happen?
Well, I guess as you take the limit where the ADS radius is going to infinity, I guess it gets ungauged in the bulk.
What does that mean? That sounds very strange.
Well, I mean, because look, you always have this, you certainly have a global symmetry, right? Now, why is it that having a global symmetry in ADS doesn't offend people? Because you interpret it as, I guess, an isometry, or you interpret it as a global symmetry on the boundary, right? And then usually the
We don't
reason
have the global symmetry in ADS, it's always gauged.
on the boundary it's a global symmetry. So it's an
That's the
isometry.
global
Yeah,
symmetry.
so it's an isometry.
No, not in general, only for highly supersymmetric cases is it an isometry. In general, just we can have global symmetries that are not geometrized by the compactification.
Okay,
And they're still gauged.
Okay, but by definition, you always have the same symmetries on the CFT and quantum gravity, right? And so because the CFT is global symmetry, ADS quantum gravity also is global symmetry.
It's always gauge symmetry.
No, a proper global symmetry. I mean, like, it's always this, you always have to have the same symmetries on both sides. Like the symmetry doesn't disappear when you go to global. So like, there was always a proper S24 global symmetry on both sides. Just the interpretation is different. So like in the CFT, it's this conventional, symmetry of the quantum field theory, and the gravity theory, we think of it as an isometry of the system. So when people make claims about quantum gravity not having global symmetries, they're always only ever talking about flat-space quantum gravity. Because in ADS, you always have global symmetries. Whenever you have supersymmetry. And so the difference, so this only becomes an interesting question when you start looking at flat-space quantum gravity. And so in flat-space quantum gravity, the standard ADS 5 crosses 5 case, the R symmetry basically goes away in flat space, so that you really do get quantum gravity with no global symmetries. In contrast with this pure quantum gravity, this weird theory, the global symmetry does not go away when you take the flat space limit. And so this is why it conflicts with the lure of the Swan point. And so that's why
I think I disagree with this sort of interpretation, but I think I disagree with them.
Okay. So perhaps you disagree with them. I'm merely quoting the results. This is not my paper. This was merely the results of these learned people.
Agree with a disagreeer doesn't make an agreeer.
Okay, anyways, so another interesting fact I wanted to focus on, and this relates to something Saab was asking about, whether we needed supersymmetry. So what happens if we relax the amount of supersymmetry in this comparison between general bootstrap bounds and 1/n expansions of known theories? So let's look at 3D and let's relax the supersymmetry from n equals 8 to n equals 6. The next lowest case. So we did the numerical bootstrap with my wonderful co-authors a couple of years ago. And in that case, we were able to compare to known CFD data, known from localization for known theories. And lo and behold, once we relaxed the supersymmetry, we now found that the theory that was saturating the bound, and this was a non-perturbative comparison. So we were comparing non-perturbative localization data to bounds. We found that the thing that now saturated the bound was this APJ theory with gauge group U1 plus n cross 1 and turn Simon's level 2n. And so what is the quantum gravity interpretation of this CFT? Well, at large n, this is supposed to be dual to higher spin gravity. Because basically at large n, this U1 guy you can basically forget about, so then it has like vector degrees of freedom. And this is, the classic results of like Sheehan et al. About ABJ triality. And so it seems that like the moment you are allowed to have a CFT with vector degrees of freedom, that's the thing which wants to saturate the bound. And so you just didn't have that for maximal supersymmetry, and that's why it wasn't saturating the bound. But the moment you allow something like that, it then saturates the bound. And this is actually consistent with what we've known from the bootstrap for many years, because after all, people studied critical ON models in 3D, and indeed those saturated the bound. So that's another example of a vector model saturating the bound even with no supersymmetry. But of course, interacting vector models only exist in 3D. So in 4D, we know that there are no interacting vector models. They're just three theories. There's no critical ON model in 4D. And so whereas in 3D, there was the possibility of something other than, Einstein gravity saturating the bound. In 4D, I don't even know of something else that would saturate the bound, even once you get rid of supersymmetry. And that's why I conjecture that if one were to do the numerical bootstrap of the stress tensor correlator in 4D, even without supersymmetry, I would still think the thing that would saturate the bound in the large C regime would be pure gravity without supersymmetry. And so I think something very nice to do would be to compute this 1/c prediction from pure gravity, which could be done. You don't need supersymmetry for the calculation. So just compute that in a 1/c expansion, getting one loop from tree level as usual. You'll have some prediction, then do the numerical bootstrap for finite C, do the comparison in the large C regime as we did. And my conjecture is that the thing saturating the bound will be this pure gravity theory. So this is something I think would be very nice to do in the future. It's more complicated because you have to deal with all these indices now because you can't look at a scale of superprimary. But I think in principle it could be done. And it would be very intriguing if this was the case, because this would be something very special about 4D CFD, because I would not expect this to be the case in 3D. Okay, so that's that.
So maybe, are there any questions for the speaker?
So this last thing about 3D CFTs,
Yeah.
like you find it saturating the bootstrap bounds even for finite C, like this.
Yeah. So yes, because basically there's a certain OP coefficient we can compute exactly using localization. And so we can just plot like the exactly known values, for discrete values of n. And we find that even down to the smallest possible value of n, it seems to be right along this numerical bootstrap. So this was unlike the case of maximal supersymmetry, where like the known values were always somewhere within the allowed region. So now it's really like, I can show you the plots afterwards, it really seems to be right along the boundary.
It's somehow the opposite of the intuition we might have guessed from gravity, that you would have to have the sphere. If things will go back. Things look better without the sphere, without the internal space.
Yeah, well, yeah, so this is what's very, curious about this, is that like, it turns out that like the fewer KK modes you have, kind of the closer you get to the boundary of the allowed region. And like, I don't know why it was obvious that had to be the case.
But can you see what the minimal massive content has to be for the theory to even make sense?
That's something you could probably determine just kinematically, I would guess, because you just have to see like can it have maximal supersymmetry or not? And like that, there's probably only very few, like I think as far as I understand, I think the only allowed KK mode spectrums is like everything, only even KK modes or no KK modes. I don't think it's consistent just to have like every third KK mode or something. I think that would break the supersymmetry further. So for instance, in the 3D CFT context, where you have like say M theory and 84 cross 7 mod ZK, you can have K be any integer, but the moment K is bigger than 2, that breaks supersymmetry below maximal supersymmetry. And so if K is 3, you'd be looking at every third KK mode, but then that doesn't preserve maximal supersymmetry.
You didn't do the experiment in 2 dimensions.
Okay, so
There's
yes,
no maximal.
there's no maximal supersymmetry in 2 dimensions. Yeah, so like also a lot of funny things happen in 2 dimensions.
Well, this maximal supersymmetry on the field theory side is free,
No,
as far as we know.
Oh, yeah, there's no known. Well, even kinematically, wait, can you define an interacting theory in 2D with maximal supersymmetry? I thought
Not
no.
interacting, but you
Yeah, you can't have interacting. Yeah, so like
we
we
don't
only
have global formulas. Like T8 mod Sn, T8n mod Sn will be maximal. But suppose there were one, we just didn't know it.
But there'd be no point of doing that, because if kinematically we know it doesn't exist, that means like if you did a bootstrap of maximal supersymmetry in 2D, presumably you would just get trivial results. And maybe you could even derive that.
Yeah, I think that one, it's more straightforward from the super algebra.
Just to show that.
And you got the same question about 5D CFT. 5D we also know that there can't.
Well, right, so I don't have a strong opinion about your conjecture about the pure radius and for dual to a 3D or 4D CFT, but for 60, I think it's like very narrow, the gap that you have to walk through to have such a thing.
Yeah, and look, and indeed, the numerical evidence is weakest at 60.
Yeah.
So I was very open.
Let me make one, just since you brought up 5D, let me make one comment about that.
Yeah.
So, one of the reasons for being more convinced about the classification in 60 is precisely because 5D maximal supersymmetry, there's no conformal generalization of it.
Yeah.
So if you take this putative 60 theory, whatever it is, you can put it on a circle that preserves all supersymmetry, and you can look at what is the long distance limit of it.
Yeah.
It will have to be some 5D theory with 16 supercharges.
Sure.
If it's unless it is a strongly coupled scale but not conformally invariant theory, which is very, very, very exotic.
Yeah.
Then it's Yang-Mills because it's free.
Yeah, but I would say that's kind of analogous to the argument that every known Yang-Mills theory in 4D is one of the ones we know about.
No, it's not, because here there's a kind of direct proof. This is not saying that like I don't have to start with anything I know.
Yeah.
I can just say that I can, once I put it on the circle,
Yeah.
then because there isn't any possibility of an interacting CFT with that many supercharges in 5D,
Yeah.
then it has to be the free one.
I see.
Yeah,
Yeah.
that's the difference.
So perhaps, I think that would actually be very cool if it turns out 60 is different from 3D and 4D. It's like,
Yeah.
I'm not committed to my conjecture being true in every dimension. I think it would be actually more interesting if it was only true in 3D and 4D, not true in 60.
Yeah, I think there's much more wiggle room in 3D and 4D because precisely because it's more like, what do we know? What are the ones we know how to construct?
Yeah, and so that might actually be consistent with what we're seeing, because just to remind the audience,
Yeah.
in 6D, in that case, it was actually very hard to distinguish between
Uh-huh.
the pure guy and the known guys. And it's like, reasonable that maybe, this orange line really is saturating the balance. No, sorry, not just the orange line, maybe the blue line, maybe the 87 crosses 4 mod Z2. And so it could be that like in 60, unlike 3D and 4D, a known theory is saturated. Which would also make Rosselli happy.
I mean, even if you don't know anything about, even if you assume no KK modes,
Yeah.
no additional fields with masses of order, MADS, whatever LADS. Are you forced to see modes with either Planck scale or string scale in the game? Do you see oscillators in the N=4 case, or do you see in M theory some analog of that?
It's a good question. I don't know the answer. But the only thing I know is about the light single trace spectrum. Like beyond that, I don't have any detailed knowledge about this pure supergravity thing. In a sense, like, the only thing I really know about it, in a sense, is by conjecturing that it saturates the bound and then like reading off, from the fit. So like indeed, it's a question of like, I mean, if this thing really existed as UV completion, like what would it even mean? I mean, like, would this be some theory of quantum gravity independent of string and M theory? I mean, like, that would be kind of crazy, but I mean, who knows?
Another question is, do you think it is possible by studying the models where there is a sphere that you could work your way back? Suppose you could compute the first non-supersymmetric correction.
D8
Yeah.
Yeah.
Do you think you could work your way back to say what it is in 10-dimensional flat space or 11-dimensional flat space?
Yeah, exactly. Yeah. So I mean, So I mean, that's kind of like one of the major points of this whole program is that there's a simple way of going from higher derivative corrections on ADS cross S to higher derivative corrections in flat space. So and so like one of the goals of the program is to compute these corrections on ADS cross S from the CFT maybe, and then plus learn about it in flat space. And so particularly the goal is to get D to the order. Now, one thing which is actually very intriguing in 3D is that in 3D, it turns out that if you really, so for these semi-short operators, these A operators, if you knew like somehow the exact answer for these A operators for like a few spins, that would be sufficient to fix D to the order 4. This is a kinematic statement that like you basically do a calculation and you see like what data do I need in order to fix the 1 over n expansion to this order, and it turns out you can learn it just from these semi-short OP coefficients. You don't have to know anything about the long multiplets. This is unlike 40 and 60, where you would need to know CFT data of unprotected guys to get D to the order 4. So 3D is kind of our best context to learn about D to the order 4. And if somehow we could think of some argument about how to compute these semi-short OP coefficients analytically, then we would derive the D to the order 4 correction. But what's really intriguing is that this statement of that from semi-shorts you can learn about high derivative corrections, this only works up to order D to the 10 R to the 4. So D to the 8 R to the 4 and D to the 10 R to the 4 you could fix from semi-short data. Beyond that, you would need long data. And that's kind of intriguing because there's some very old conjectures by various people, maybe even some people in the audience, that in M theory, only certain higher derivative corrections should be non-zero. So in particular, there was like conjectures that it would only be like D to the 6n R to the 4 for integer n. So R to the 4, D to the 6 R to the 4. I mean, these reasons aren't totally justified. I mean, like, so like one conjecture is from Nikolai et al, where he has kind of like E, whatever, like 11 symmetry. And like, if that symmetry makes sense, and if you impose it, then it only allows these specific terms. Another kind of curious fact is that we can look at the data which we do know non-perturbatively in it. So for instance, in 3D, we know this OP coefficient we can compute from localization non-perturbatively. And if you expand that in C, you only find the powers of C corresponding to this conjecture. And this isn't totally, you might say, okay, fine, but that's some protected quantity. Maybe that's why you're only finding those terms. But if you expand the analogous quantity in 4D, so if you expand the mass form free energy in 4D in 1 over n, then you actually do find non-zero coefficients for every single term, including D to the 8 R to the 4, D to the 10 R to the 4, etc. And so there seems to be a qualitative difference, even in this protected data, between 4D, where we know D to the 8 R to the 4 is non-zero from weakly coupled string theory, versus 3D and 60. Because you can also expand the 2D Kyle algebra data at 60, and it also only shows specific powers of C. And so there's some kind of like perhaps coincidental evidence suggesting that maybe the M theory low energy expansion is really drastically simpler. And if that's true, that'd be really amazing, And like, I mean, there's all kinds of crazy conjectures. We want to actually just confirm these conjectures at D to the 8 R to the 4. So like our goal is to like numerically argue that either D to the 8 R to the 4 is 0 or not. And then if it's really 0, then maybe we should take Hermann Nikolai more serious. We should take him seriously anyways. But even more serious.
And so maybe we'll keep further questions for later and we'll have the speaker doing that. Stop the recording before.
You I was just wondering about playing this kind of analogous compactification game between 3D and 2D. You take a 3D